Welcome to part 2 of my lecture series on pressure-based coupled algorithms. In this part of the lecture series, I'm going to be focusing on the pressure equation and showing you how it's incorporated into the coupled matrix system. There are some intricacies involved, and I really want to highlight these in this talk so that you have an even deeper understanding of how the pressure equation is included in the coupled algorithm. I'm also going to be wrapping up this talk by talking about some common recommendations for whether you should choose to use the coupled algorithm or whether you should just go with a standard segregated algorithm like the simple or piezo algorithms. They're going to follow at the end of this talk. All right, let's dive in and start by looking at how the pressure equation is incorporated into the coupled matrix algorithm. In order to understand how the pressure equation is included in the coupled matrix equation, we need to start by thinking about the continuity equation. And I want you to think about the steady continuity equation, so without the time derivative term. And in vector form, of course, the continuity equation is just the divergence of rho u, where rho is the density and u is the velocity field, is equal to 0. And what we're going to do is we're going to use the finite volume method to express the continuity equation in a discrete form that we can use in the CFD code. And the way we always do that in the finite volume method is start by integrating the equation, in this case the continuity equation, over the volume of a general cell in the mesh. And because the continuity equation is equal to 0, its integral over the volume of a cell is also equal to 0. And the reason we start with the volume integral is we can use the divergence theorem to convert the volume integral into a surface integral, and that's ultimately what will allow us to write it in algebraic form. So we're starting with this volume integral here on the left, and then the divergence theorem, what that says is that the volume integral of the divergence of rho u is equivalent to the surface integral of the unit normal vector dot product with rho u over the surface. So the surface being the entire surface of the cell. And physically what this is saying to us is that the accumulation of this quantity within the volume is equal to the flux of the quantity over the surface. But I like to think about this as transforming this volume integral into a surface integral. And the next thing that we do in the derivation and the simplification is to note that our cells in our mesh, of course, these are physical cells with flat sides. We don't have a smooth, continuous surface. The divergence theorem will apply to any enclosed surface. We have a cell that has a finite number of flat faces. It's a polygon. And so rather than having the integral over the entire continuous surface, we can just split that into the surface integral over each of the faces of the cell in turn and sum them together. So that's why we can go from equation 3 to equation 4. We're just saying instead of integrating over the surface, let's integrate over each of the faces and then add them up. And the next thing in the simplification, we use the same technique that we used in part 1, which is remembering that all of the flow variables vary linearly across the faces of those cells. So now we can simplify each of those face integrals. And the way we can do that is once again by noting that because we have that linear variation across the face, the integral over the face will just be equivalent to the value at the center of the face multiplied by the face area. Or you can think about this visually as the area under the dotted line is equal to the area under the solid line. And it actually doesn't matter what the gradient is. You could change the gradient of that line as long as the value is pinned at the middle. The area under the solid line will always be equal to the area under the dotted line. And so we can simplify the integral over an individual face into the value at the face center, which I'm denoting with the subscript f, here multiplied by the face area, and we still have to sum over all of the faces because the value at the center of each of the faces will be different. So this is just our simplified continuity equation, which is written in terms of the quantities at the center of each of the faces of a general cell in our mesh. And the next simplification that we can do is just by looking a bit more closely at that simplified continuity equation. And the thing we notice is that we've got a dot product between the unit normal vector and the density and the velocity field. And of course the density is a scalar, so we can just bring that in front of the dot product there, which allows us to slightly rewrite our discrete continuity equation in this form. And this is really useful because it actually helps us with the interpretation. Because what I've done so far are quite a few mathematical tricks and mathematical techniques, but when we write it in this form, this allows us to regain a lot of the understanding of what we've actually done here. And the key to that understanding is to look at the terms closely, and if we start in the middle, we can see we've got the dot product of the unit normal vector and the velocity at the face center. So if we think of a general cell and a general mesh, and we think about the face center, we've got a velocity vector there. And of course the velocity vector, UF, can point in any direction it wants. It's part of the solution. But the unit normal vector always points normal to the face out of the cell. So when we take the dot product of that unit normal vector and the velocity field, what we're actually doing is getting the component of the local velocity that's normal to the face. And the reason that's important is the component of velocity that's normal to the face transports mass across the face of the cell. And of course, if we multiply the dot product of the unit normal vector and the velocity vector with the density and the area of the face, you can think about this as the velocity field along the face. Each part of that velocity field is transporting mass across the face, and all of that together will give us the total mass flow rate that's passing out of the cell across the face. So what this quantity is really saying to us is that the summation of all of those face mass flow rates across each of the faces of the cell must equal 0 for the continuity equation to be satisfied. And that's a really useful result. If you want some further confirmation that this is actually what's happening, imagine the case when that face velocity vector is parallel with the face. If you imagine the velocity is just running parallel to the face, it means that the flow field isn't transporting any mass across that face. The flow is just running parallel to the cell, so no mass is coming in or out of the face. It's only when that velocity field crosses the face that it's going to start transporting mass in and out of the cell. And that's why that dot product is really important here. And we can think about this unit normal vector, in a little bit more detail as well. It tells us some further detail. Because the unit normal vector always points out of the cell, then it tells us that if we remember some of the properties of our dot product, if the dot product with the velocity field is greater than 0, that's telling us that the velocity vector is pointing out of the cell. But of course, if the velocity is pointing in the opposite direction to the unit normal vector, then the dot product will be less than 0. So the sign of the dot product is actually telling us whether mass is going in or out of the cell. And of course, if the dot product of the unit normal vector and the velocity is exactly equal to 0, that's because the velocity is perpendicular to the normal vector. There's no mass crossing the face and we're not getting mass passing in or out of the cell. So this dot product is really powerful. It's giving us lots of information and it's really useful for us with the continuity equation. And if we think about a particular cell, if we evaluated this quantity, rho f, multiplied by the dot product of the unit normal vector, the velocity field and the face area vector, we might find a situation that's like this, where the face at the top has plus 3 kilograms per second, the face on the right has plus 7 kilograms per second, so we know that there's 3 kilograms per second and 7 kilograms per second passing out of that cell across those faces. And then over these two faces, because the velocity vector is pointing inwards, we actually work out that there's minus 4 and minus 6 kilograms per second going into the cell. And we can clearly see just by looking at this cell that the continuity equation is going to be satisfied. Mass is going to be conserved. The amount of mass passing into the cell across those faces is equal to the amount of mass passing out of the cell. And that's what the summation is telling us. That's why the summation is equal to 0. But if we looked at this cell on the right, you can see that there's a lot more mass passing out of the cell than there is going in. This summation would not be equal to 0 and the continuity equation would not be satisfied for this cell. So even though we've done a lot of mathematical work, a lot of mathematical techniques to transform the continuity equation into this form. We've still got all of the understanding, and this is still clearly a representation of conservation of mass. So this is fantastic so far. We've really understood the continuity equation, but what we really care about in this talk is how is mass conservation included in the coupled matrix equation. That's what we really care about. And what I want you to do is just to take a step back and think about what we were talking about in part 1. So let's take a step back and think about where we were when we'd only considered the U and V momentum equations for the example mesh with 4 cells. So we've got conservation of momentum in the X and Y directions. The U momentum equation sits along the top here, and the V momentum equation sits along the bottom. And we haven't considered the continuity equation or the pressure equation yet. And remember from part 1 that if this block matrix system seems a bit intimidating or confusing, the easy way to remember how to interpret it is to just focus on a single row of the A matrix, which will represent a conservation law for that particular cell in the mesh. So for this top row, this is conservation of momentum in the U direction, the X direction for cell 1. And if we just read across and then down, we can see we've got A11 U1 plus A12 U2 plus A13 U3, A14 U4. No contribution from V because the U and V momentum equations are independent. And then we've got the minus A11, A12, A13 and A14, P11, P2, P3 and P4. This is the implicit contribution of the pressure gradient force that we looked at before. And then we've got the source term on the right hand side. And the first 4 rows are just conservation of momentum in the U direction for cells 1, 2, 3 and 4. And then those final 4 rows are the V momentum equations there. And those extra terms were the implicit form of the pressure gradient. So how could we incorporate the continuity equation or the pressure equation into this coupled matrix equation? Well, the key is to remembering the implicit form. We used an implicit form to incorporate the pressure gradient terms there in the U momentum equation. We're going to have to do something similar. So how could we write our continuity equation in implicit form? And that would allow us to put it in the coupled matrix equation. Well, in the same manner as the pressure gradient force, remember before when we were working out the force from that pressure gradient, we ended up with an equation for the pressure at the face center. Well, we have the same thing with the continuity equation. Our continuity equation depends on that velocity vector at the center of the faces of all of the cells. But of course, we're using a collocated finite volume method. We only know the velocities at the cell centroids, and the unknowns in that matrix equation, that coupled matrix equation, U1, U2, U3, U4, these are the velocities at the cell centroids. So we need to use interpolation to rewrite that face velocity in terms of the velocities at the centroids on either side of the face. And we can use the same general equation for interpolation that we used before, where we use omega, which is like the slider between those two values, and omega will depend on the type of interpolation, but it's completely general for this task. So we've got our 2 equations. We've got our continuity equation in discrete form, and we've got our equation for linear interpolation. And if we combine them together, if we just pull these 2 terms in for UF, which you can see there in equation 10, and then split the summation up into a summation for UP and a summation for UN, we arrive at equation 11. So that mathematics is quite straightforward, but we can see that it's starting to look a little bit intimidating. We're starting to have quite a few terms here. Things are starting to get a bit out of control. How can we proceed? Because remember that we need the components U and V at the centroid of those cells in the mesh. How do we proceed? The key to the next stage in the derivation is actually to expand the dot product of the unit normal vector and the velocity vector. And you remember that for the dot product, what we do is we just take the components of the vectors and we sum them together. So we've got the x component of the unit normal vector multiplied by the u component of the velocity vector, and plus the v component, the y component of the unit normal vector multiplied by v. And if we were in 3D, we could of course extend that. So then we substitute that in for those dot products in the continuity equation, which you can see there. And then all I've done to go from equation 13 to equation 14 is to split the summations up. So this has become 2 summations, this has become 2 summations, and we arrive at equation 14. So the maths there is fairly tedious. You've got a lot of terms to look after, and you can always stop the video and go through the mathematics yourself if you want to. You'll find you arrive at the same formula that we've got here. But what I want to do is just run through a quick example to convince you that this is the correct formula to use, and it will help us in the understanding of how we're going to develop that coupled pressure equation. So let's look at an example. I'm using the same example that I used in part 1, where we've got this central cell, cell 1, surrounded by 4 other square cells. The cells have face areas of 1 meter everywhere. All of the cells are equidistant between each other. The density is 1, and the interpolation fraction that I'm using is just a half. We're just taking averaging. We're using linear or distance-based interpolation between the two centroids to get the velocity at the face centers. And remember, of course, that the unit normal vectors point out of the cell, and they're at the center of all of those cells, which you can see here. And we're going to evaluate this formula. And most of the terms, the density is going to be 1, the area is going to be 1, they're going to disappear. The omega is going to be equal to a half. And so the only difficulty here is really just keeping track of the components of those unit normal vectors and multiplying them by the correct velocity components at the face center. And feel free to stop the video and go through the example for yourself. But what you'll find, if we just look at this first summation, UP, the cell we're considering, P is cell 1, so we're going to have U1, and then the summation, we're going to have a half on all of the faces, 1 for the density, 1 for the area, and then nx, that's the x component of the unit normal vector, is 1 on the right and left faces, and it's equal to 0 on the top and bottom faces. So you can see we have a half, 0, minus a half, and 0 there, because we have the -1 for the unit normal vector. And then we can carry on and do the same thing for each of those summations. And if you run through all of the terms, you'll have equation 15 there. And then all I've done is just collect together each of the terms. So we've got the half U1 there, which cancels with the minus a half. We've got a half U2 minus a half U4. We've got that, those terms cancel out, minus a half V3 and then a half V5. And that allows us to write our continuity equation in this simple form, which you can see there, equation 16. And just looking at it, what does it say? We've got a half U2 minus a half U4 plus a half V5 minus a half V3 is equal to 0. And of course, a simple solution to this, if you're looking at it, is that if U4 is equal to U2 and U3 is equal to, V3 is equal to V5, of course, the mass coming in across these faces will be equal to the mass going out across those faces. So this does still represent continuity equation, conservation of mass, as we can see. But what I really wanted to emphasize for you with this example is that you can see that actually the continuity equation can just be written in this general form, where we've got a coefficient multiplied by U1 plus a coefficient multiplied by U2 plus a different coefficient multiplied by V1, a different coefficient multiplied by V2, all the way through for all of the cells in the mesh, and that's just equal to 0. We can write the continuity equation in this general implicit form, and you'll notice it's very similar to the implicit form of the pressure gradient that we had in the previous talk. And we could go through if we wanted and be really rigorous and work out what the definition of the coefficients C1, C12, D11 were from this general formula, but it's not really necessary for our understanding of the coupled equation. What I want to do now is insert this equation into the coupled matrix equation. So you can see what happens when we have the U momentum equation, the V momentum equation, and then the continuity equation straight after. So what happens? We've got the 3 blocks which are inserted on the bottom here. And remember, the trick with the coupled matrices, as always, is to look along a row of the A matrix. And so if I look, this is the continuity equation for cell 1. And you can see we've got minus C11 U1, minus C12 U2, minus C13 U3, minus D11 V1, minus D12 V2 through. But then we've got 0 for P1, P2, P3, and P4. And our source term is also equal to 0 on the right-hand side. Looking at that continuity equation, pressure doesn't enter the continuity equation at all, and we've got no term on the right-hand side there. So what this results in is zeros in that block diagonal of our coupled matrix and on the right-hand side. And if you look through the literature for pressure-based coupled systems, you'll often see this referred to as the saddle point problem. And I don't want to go into too much detail about what that actually means, but for us as CFD engineers, all we need to understand is that this matrix equation is going to be difficult, or if not impossible, to solve with a numerical algorithm. Even if you think of a technique like the Gauss-Seidel or the Jacobi algorithms, where we divide by the diagonal coefficient of the matrix, we've got zeros on the diagonal. That algorithm is not going to work to allow us to solve the matrix system. So this isn't a good way for us to formulate our coupled matrix system. And this is why I wanted to show it to you. I wanted to show you that if you have the U momentum equation, V momentum equation, and then if you put the continuity equation in directly to the coupled matrix system, treating it implicitly as you might expect, you can't formulate the matrix equation in this form. You have to do some more work. And that's what I want to focus on in this talk. So we can't use the continuity equation directly. What do we need to do to allow us to formulate this coupled matrix equation correctly? Clearly, we need to have some method of getting the pressures involved in that matrix equation for cell 1, and we need some way of getting a source vector there. And the key is to use the Rhie and Chow correction. Now, some of you may remember that the Rhie and Chow correction is used in segregated algorithms, and it's applied explicitly to correct the mass source in the pressure correction equation. Well, it turns out that the Rhie and Chow correction also needs to be applied in the coupled pressure-based solver as well, but it's applied in a different form. And the way that it's typically applied is by combining the Rhie and Chow correction with the continuity equation directly. And just a brief recap of what the Rhie and Chow correction actually is. I do have more detailed videos on the correction itself, and you can always look through the literature on the internet if you want to find more detail. But briefly speaking, for this talk, all we need to understand is that the velocity at the face center, so UF, this is the velocity at the face center that we would be using in our continuity equation, we take the value that we calculate using linear interpolation. So that's what we used in our previous example, and that's the obvious sort of straightforward approach that you might think to use, taking the value between those two centroids. We take the value with linear interpolation, and then we subtract a coefficient dp, which we don't really need to understand for this talk, it's just a coefficient, and it's multiplied by the difference between the pressure gradient across the face and the pressure gradient interpolated to the face center. So this might look a little bit confusing, and if you want some more details, definitely go and watch some of my other videos on the Rhie and Chow correction. But for this talk, what we need to do is all we're going to do is use the Rhie and Chow correction and substitute this formula into the continuity equation, and that's going to allow us to get around that saddle point problem in the pressure-based coupled solver. So let's go ahead and do that. What's going to happen is, of course, when we put this in here, we're going to end up with three different summations. We're going to have one summation with UF replaced with UP over bar, and I've used that over bar or the overline just to indicate linear interpolation. Then we're going to have another summation with dp nabla pf instead of UF, and another summation with dp nabla pp. So there are going to be three different summations here. And I've got those for you in equation 19. You can see we've got the nabla pf and the dp here. We've got the dp and the overbar pp there, so the two pressure gradient terms. And then we've got that linear interpolated velocity, which looks very similar to the previous continuity equation that we had. And going through that previous example that I did for the example of the square cells, you'll recall that this particular term, because we calculated this with linear interpolation, we could actually write this in the general form, the C11 U1 minus the C12 U2, D11 V1 minus D12 V2. So we can rewrite that form in the general implicit form that we had before, and those are going to form those implicit coupling blocks on the off diagonals of the coupled matrix system. But the key with the Rhie and Chow correction, now that we've applied it to the continuity equation, is we've got another term on the left-hand side here, and we've got another term on the right-hand side. And the term on the left-hand side, without going into too much detail, we can actually rewrite this also in terms of the pressures at the cell centroids. And the reason we can do that is this nabla PF is the pressure gradient across a face directly. So clearly that will depend on the pressure on one side of the face and the pressure on the other side of the face. And we could repeat this and just write it in a general implicit form as A11P1 plus A12P2 plus A13P3 plus A14P4 and so on. And these terms that we've generated here are going to end up in that block diagonal of our coupled matrix system, which will ultimately allow us to avoid the saddle point problem. That's really important. And then the terms on the right-hand side, they'll just be evaluated explicitly and become the source vector on the right-hand side. So when we go back to that coupled matrix system, we can see that the off-diagonal blocks here are the same as they were if we just used the continuity equation as it is. But then we've got the non-zero coefficients on the diagonal here, which are multiplied by P1, P2, P3, and P4. And now we have the source term. So I'm hoping that without going into too much detail there on the Rhie and Chow correction itself, you can just see how it's necessary to include it. And when you do include it in the continuity equation, the coupled matrix system doesn't have any zeros on the diagonal anymore. And this is a great result. This is a fantastic result. And actually what I want to do is just make a few other simple observations of this coupled pressure equation. Again, I don't want to go into detail because I think that might be confusing and it's really beyond the scope of this talk to go into too much detail, but there are a few observations we can make which will really help our understanding. And the first observation we can make about this coupled pressure equation is that notice that the unknown variable here, the P, is the pressure itself. It's not a pressure correction. So this is very different. This pressure equation itself is very different to the pressure correction equation that you may see in some earlier literature for the simple algorithm. If you look in the textbook by Patanka, for example, the original simple algorithm uses a pressure correction field. But in this coupled pressure equation, we're using the pressure itself. So there's that slight difference there. And there's a second difference as well between this form of the pressure equation and the pressure equation that you may see in modern implementations of the simple and piso algorithms, that even though they will use the pressure directly and not a pressure correction, there are actually some differences between the terms. And this is a really subtle point that I just wanted to highlight for some of you in case you're looking into coupled algorithms in more detail. And the point I wanted to make is if we just focus on the second two terms here, if we focus on the velocity term here, which we treated implicitly on the left-hand side, and our source term there on the right-hand side, in modern segregated algorithms, like the algorithm you may see in OpenFOAM, these two terms are actually combined together. And the way those terms are combined together is by introducing a new field, which some of you may recognize as H by A, particularly if you're an OpenFOAM coder. H by A is defined as the summation of UP and then plus this dP multiplied by the pressure gradient nabla PP there. And if you make that summation into our coupled pressure equation, these two terms of course combine into a single source term on the right hand side, which depends on H by A. And the left hand side, so the unknown variable, is still the same. This is telling us that our diagonal block set of matrix coefficients for the coupled pressure equation is going to be the same as it is for the segregated algorithms like simple and piso, but actually there are some subtle changes to the source terms and those off diagonal block coefficients. And if you're an OpenFOAM user, I just wanted to draw your attention to this because it's a very subtle difference and you may notice it yourself if you're going through the source code. So just pulling out a few individual lines from some OpenFOAM source code. From a segregated solver like the simple algorithm, you'll see of course that the first thing the code does is, after solving the UV and W momentum equations, is that the field H by A is calculated. H by A is then interpolated to the face of the cell and the dot product is taken with the face area vector. and then the divergence of that field becomes the right-hand side of the pressure equation. So this is the same as equation 26 you can see here. We've got the field h by a, which is interpolated to the center of the face with the overbar, and then the dot product is taken with the face area vector, and that, the divergence of that quantity becomes the right-hand side of the pressure equation. But actually, if you look at the source code for the coupled pressure equation, you can see the left-hand side is the same. We've still got, even though there's a slight change in notation there, the left-hand side is the same, but I want you to notice that the right-hand side is different. You can see we've got the divergence of the gradient of pressure here. This is what we saw in the right-hand side of our coupled pressure equation. The right-hand side is different, and you'll see that there's some insertion of the implicit coefficients there. U in P, those are going to be the block off diagonal coefficients. But the right-hand side source term is different. There's that subtle difference there between the coupled pressure equation and the segregated pressure equation. And even if you don't take this detail any further yourself, I just want you to appreciate that there are some subtle differences here between the continuity equation, the coupled pressure equation, and the segregated pressure equation. And of course, for those of you who are doing coding or looking at algorithms in more detail, you may want to consult the references for further reading. Now, to finish off the talk, I just wanted to do some quick recommendations and comparisons for whether you should use a coupled solver or a segregated solver, which will be particularly useful for you if you use Fluent, for example, and you have the choice of pressure velocity coupling algorithms. Now, if you search online, what you'll often find is that people report that the pressure-based couple solver typically requires fewer iterations than the simple and piezo algorithms for steady-state solutions. So if you compare the residuals directly, you may find the residual plots looking something like this, where the simple algorithm takes many more iterations than coupled does to converge. And so based on that observation alone, you may think, well, the coupled solver requires fewer iterations, so it's better, and I should use that. But the subtle point here, of course, is that each individual iteration of the coupled solver is going to be slower because the matrix is much larger, so you're solving a large matrix which takes more time. So actually the metric that you care about is the total simulation time. If you're looking at speed, it's not the number of iterations. And the other point to note is because we've got that large matrix system, we have to store all of those matrix coefficients in memory, at least locally, when we're solving the coupled system. And so the memory requirements are much higher for the coupled solver as well. So it's actually not straightforward whether you would choose to use the coupled solver or a segregated solver like simple, for example, because a coupled is not necessarily any faster than the simple solver. Now, what many people report online is that, and this has been known historically ever since CFD codes were first developed in the 60s, 70s and 80s, is many people find that the segregated algorithms like simple and piezo are faster to converge and they have lower memory requirements. And this is why the segregated algorithms were pursued so heavily historically. There was lots of development in simple, simplec and simpler and piezo algorithms because they were seen as faster and more successful. And in the early days of computers, when you really didn't have a lot of memory and computers were quite slow, the importance of speed for simple problems was really important. And this is why algorithms like simple were pursued early on. However, the important thing to note here is that with a segregated solver like simple or piezo, because we're going through the equations individually, the pressure and velocity are not actually correctly coupled with each other until we have a converged solution. So early on in the iteration, in the first few iterations, pressure and velocity are only loosely related to each other. You can think of it that way, that changes in the velocity field are related to changes in the pressure field, but they're not directly coupled. The coupling is not accurate yet. And so what that means is that for some more challenging flows like turbomachinery or compressible flow solutions, for example, where the accuracy in the pressure velocity fields and the coupling between them is really important for other fields like the energy equation and to calculate density, then this can lead to convergence difficulties. And so even though it's faster, for some challenging codes, simple and simplex and piezo may diverge. So they're faster, but they're faster at diverging. And for these more challenging flows, many people report that the coupled algorithm is more stable and is less likely to diverge. And these observations that have been made allow us to make some very useful recommendations. The first recommendation, of course, is that every flow scenario is different, and actually the physics of your flow is going to affect which pressure velocity coupling algorithm happens to be most successful for you. But we can take a pragmatic approach, and a common recommendation is to try the simple or simplex algorithms first, because they are typically faster and have lower memory requirements. So they would be a good first attempt. You can see if they work, then you get your solution fast and you have your solution there when you want it. But if the convergence is poor, then you may want to switch to a coupled algorithm, which is typically slower, but it is more stable. So even though it takes you longer time, not more iterations, longer time to get there, you end up with a solution rather than a diverged solution. So for you as a user, unfortunately, this means you have to do some trial and error with your own codes and to try the different algorithms and see what works best for you. But let's wrap up with a quick summary. The important points from this talk are that the Rhie and Chow correction is needed to avoid the saddle point problem in the coupled matrix. We can't just use the continuity equation directly to formulate our coupled matrix system. And when we use the Rhie and Chow correction, this allows us to formulate a pressure equation, and the pressure equation that forms part of our coupled matrix system is different. It's slightly different due to differences in the source term to the pressure equation that's typically used in the segregated algorithms like simple and piezo. And many CFD users have found that coupled algorithms are often slower than segregated algorithms and have higher memory requirements, but they are often more stable because we have that close coupling between pressure and velocity during every iteration, not just the final iteration of the solution. And so a common recommendation is to try the simple or simplex algorithms first for speed, and if those algorithms are unsuccessful or have poor convergence, then switch to a slower and more stable coupled pressure-based matrix solver for your CFD code. So that wraps up my discussion of pressure-based coupled algorithms. I'm really hoping by the end of this lecture series that you've got a good understanding of how the coupled matrices are actually assembled from the momentum and pressure equations and how that implicit coupling finds its way into the matrix. I'm also hoping that with this new understanding, you're able to make a more informed decision about the type of pressure velocity coupling algorithms that you try and use in your own CFD codes. If you found this talk useful, as always, let me know in the comments section. I really do appreciate hearing from you. It does make all of these talks worthwhile, knowing that you're finding them really useful. So thank you again for all your support. I do really appreciate it, and I'll see you in the next video.